Hi everyone, I am really from Alibaba Group. I'm going to present the work Automated Intelligent Healing in Cloud-Scale Data Centers. This is a joint work with the Chinese University of Hong Kong and Xi'an University. Before we get started, I want to introduce some background. Cloud-scale data centers in production are susceptible to various types of component failures such as hardware crashes, software bugs, and network problems. To maintain high availability of commercial cloud services at scale, modern cloud-scale data centers often support self-healing, which refers to the automation of the detection and repair of component failures with limited human intervention. The cloud infrastructures mentioned in this paper comprises 22 data centers, includes 5,100 clusters with a total of 1.1 million servers. Our cloud infrastructures also includes a monitoring system that centrally monitors all servers in real time and collects raw monitoring logs from each server. The raw monitoring logs covers 165 attributes, which describes the operational states and error information of a server. Each attribute is associated with one of 6 levels of failure severity, namely info, good, warning, error, critical, and fatal. Our cloud infrastructures support 6 different repair actions to fix a failed server. These repair actions are also commonly used for self-healing in other production data centers. Given the limited number of repair actions, one might ask, is it feasible to traverse and try each repair actions to fix a failure? Unfortunately, the answer is no, as executing a wrong repair action as extra overhead and increases the server downtime. Therefore, we need to find the most suitable repair action for each failure to minimize the downtime of each failed servers. Our cloud infrastructures has adopted a policy-based self-healing solution. However, our deployment experience is that policy-based self-healing is ineffective due to the huge number of attributes and different severity levels of each attribute. Our policies currently can only cover the small fractions of failures for some combinations of severity levels, but cannot cover any emerging failures that we have not observed. This motivates us to explore machine learning-based solution to automate the entire self-healing workflow. The existing study reported adopts machine learning to predict the repair actions based on historical data. While machine learning is well believed as an effective tool for data-driven prediction, there remains limited analysis of machine learning-based self-healing solutions in real-world cloud-scale data centers deployment. In particular, some key deployment questions are unexplored, such as how a complete machine learning-based self-healing pipeline should be deployed, how the prediction accuracy of self-healing varies across different machine learning models, how different stages of machine learning-based self-healing pipeline affects the overall prediction accuracy of self-healing. We answer the above question in this paper. Our contribution is AIHIS, an automated intelligent healing system that applies machine learning to self-healing in cloud-scale data centers. AIHIS provides a full-fledged general pipeline that supports various machine learning models and predicts a repair action for a given failure based on the learning of raw monitoring logs and historical repair action. AIHIS is currently deployed in production cloud-scale data centers with about 600,000 servers at Alibaba Cloud. To validate the effectiveness of AIHIS, we conduct extensive evaluation via both trace-driven and production experiments. To motivate the AIHIS design, the monitoring system collects a repair record of each triggered repair action. Each repair action contains the following fields. Firstly, the server ID. Secondly, the raw monitoring logs. Thirdly, the triggered repair action. And finally, the repair result. The repair result is marked as either successful if the repair action successfully recovers the server. Figure 1 shows the architecture of AIHIS, which comprises 3 components, namely mapper, predictor, and the controller. As machine learning requires numerical features for training prediction, we first design the mapper that transforms the raw monitoring logs into numerical features. The mapper formulates the transmission as an embedding problem in natural language processing, where the raw text is processed by unsupervised learning models and converted into numerical vectors. We further designed the predictor to recommend one of the repair actions for each detected failure. Specifically, it receives the numerical features of a failure from the mapper as input. It then predicts a repair action, which is sent to the controller as a recommendation. The predictor formulates a multi-class classification problem in which each class corresponds to a repair action. Finally, we designed the controller to take the numerical features as for a failure from the mapper and the recommended repair actions from the predictor as input, and determines the final repair action to fix the failure. To find a repair action that is most likely to fix the failure, we design the controller to assess the recommended repair action on the failure to see how likely the repair action can fix the failure. To assess the repair action of a failure, the controller employs 6 trained binary classifiers, one for each of the 6 repair actions. Each binary classifier learns the relation between the monitoring logs and the repair results of a specific repair action. The controller executes a 3-step workflow. Firstly, it feeds the numerical features of the failure into the corresponding classifier of the recommended repair action made by the predictor and predicts the repair outcome. If the repair outcome is successful, the controller directly triggers the recommended repair action and quits. Secondly, if the repair outcome is predicted to be unsuccessful, the controller assesses other repair actions. It first assesses the repair action that has lowest repair cost. If the repair outcome is predicted to be successful, the controller triggers the repair action and quits. Otherwise, it repeats the assessment on the next repair actions with a higher repair cost. If the controller finds no repair action that returns a successful outcome, it calls the administrator to manually diagnose the failure. We train the machine learning models offline for AIHIS before its deployment. For the predictor, we train its multi-class classifier using successful repair records. For the controller, we train each binary classifier using both successful and unsuccessful repair records. Also, we periodically update the models of AIHIS in deployment. We now check whether the model accuracy can be improved with the new repair records on the monthly basis. If the new model shows improved accuracy than the old one, we update the deployed AIHIS with the updated model. For deployment, we have deployed the AIHIS on 2,020 200 out of 5,100 clusters. We divided the 2,200 clusters into 5 groups based on the services hosted by the clusters. Each group runs an AIHIS instance independently. We evaluate AIHIS with extensive trace-driven and production experiments. We first compare the unsupervised learning models in the mapper by studying how they affect the prediction accuracy in the predictor and the controller. Specifically, we fix GBDT as a multi-class classifier in the predictor and the binary classifier for each repair action in the controller. Our results show that LDA is the most suitable model for the mapper and provides a high prediction accuracy in both the prediction and the controller in our context. We next compare the multi-class classifiers in the predictor. We fix LDA in the mapper and compare the accuracy of different classification models in the predictors. Our results show that GBDT achieves the highest precision, recall, and F1 score in all cases. One major reason is that GBDT can better solve the simple imbalance problems of our collected traces. We compare different binary classifiers in the controller. We again use LDA in the mapper. For each repair action, we train the corresponding binary classifier using all the related repair records. Both GBDT and RF generally achieve the highest accuracy. Nevertheless, for the sake of simplicity, we tend to choose a single model for all repair actions. We find that GBDT performs best for most repair actions. Thus, we also chose GBDT for the controller in our deployment. We next benchmarking different components of AIHIS. Before that, we defined the metrics of evaluating accuracy of AIHIS, namely hit rate, reverse rate, and overall rate, where the matrix is similar as precision, recall, and F1 score. Here, we use LDA in the mapper and GBDT in predictor and controller. Our results show that if any component is disabled in AIHIS cannot work perfectly. In contrast, combining all components to learn both successful and unsuccessful repair records allows AIHIS to achieve high hit rate, reverse rate, and overall rate. We then study the production accuracy compared with the policy-based self-healing solution. This figure here compares the success rate of both approach, where the success rate is defined as the fraction of prediction failures that are successfully fixed. We observe that AIHIS significantly outperforms the policy-based solution all the time. Consider 7 months. AIHIS successfully fixed 92.4% production failures over 7 months. Furthermore, AIHIS also reduced 51% of unavailable time of each failed server compared to the baseline. We also study how monthly update improves the accuracy of AIHIS. Figures compare the accuracy when we enable or disable the monthly update mode mechanism. We find that disabling monthly model updates significantly reduce the F1 score of predictors and the overall rates of AIHIS. On the other hand, enable monthly model updates allow us effectively mitigate the impacts of emerging failures and maintains high prediction accuracy. Finally, our current deployment treats each AIHIS instance independently, such that the model training of each instance is independent of the other instance. We justify this deployment strategy by studying how the repair records collected from different AIHIS instances affect the accuracy of each AIHIS instance. This table shows the results. We observe that each instance achieves a higher overall rate when only use the repair recorders collected from itself to retrain the models. Aggregating repair recorders from all 5 instances to retrain the model actually reduce the overall rate of each instance. That may be because the repair recorders collected from different AIHIS instances have different statistical properties. We now post some lessons we learned from the design and deployment of AIHIS. Firstly, designing AIHIS as a general framework allows us to find the appropriate machine learning models for self-healing for different deployment environments in our business. Secondly, in our cases, LDA can better interpret the correlation among different attributes and thus achieve best accuracy in mapper. While GBDT achieves high accuracy in prediction and controller as it can solve simple imbalance. Finally, performing incremental deployment of AIHIS on our business and monthly model update for AIHIS, which allow us to observe if AIH works as expected. To conclude, we propose AIHIS, a machine learning-based automated intelligent healing system for cloud-scale data centers. Our project is now open sourced for further research. That's all. Thank you.